What we want to finish off with this morning is just to go through some of the terminology which raises some of the issues about actually modelling itself. I will come back to the issue of how you drive these models, especially from the greenhouse gas side next week on this equivalent lecture next week. And I'll give you some more material to do so we can talk about those when we go through in part 2. But what we're doing now is sort of leaving that to one side and going back to some of the basics about how the models actually operate. So the variables that keep a climate model keeps track for each part are known as the model state. So the state of a model determines the variables that we use. Not all models use the same variables. So models have different states. And why would some models have different variables or possibly give different weights to different processes than others? We're talking about a general climate model, atmosphere, ocean. We've talked about the basic principles of the atmosphere and the ocean. What? You're in Exeter, Hadley Centre, Met Office. You're in Hamburg. You're in NCAR in the US. You're in Beijing.
Is relevance to where?
Sorry?
Is it like rate it so it's more relevant to where you are?
That's a possibility, that if you're more interested in, say, drought, mid-latitude problems rather than global temperature, then yes, that would influence the way you would determine what you use. That's a possibility. What else would determine it?
BCC, don't they just run a lot of models and then there's like a cluster that kind of come out at the same place?
Yeah, I'll talk about that next week. But that reflects the fact that all the models that are being run are slightly different because they have different ways of modelling the Earth. And I'm trying to get you to think about why you think there may be differences, because you talk about truth and reality and that the world is real. So surely everybody's trying to do it the same way, because
Everyone has different understandings. Like, obviously, there's not one answer to how everything works, so they have to try different ways in which it works.
yeah, if you go to people, they will say, we think that the principal driver is ocean storage of heat or whatever, and we want to model that better. So if we're going to model the ocean by looking at the ocean in 5 blocks with depth, that will give us a better idea of the oceans. Whereas another group will say, well, we're going to simplify the ocean because we prefer to put that detail in the atmosphere, or we prefer to look at that detail in the transfer processes between the three. Now actually, and when you boil it down, the reasons behind that are often cultural, because this is what the Germans have always done. This is their approach. They've always done. They're coming out of an institute which is very ocean-based, therefore they feel confident in their modelling of the ocean, so they'll simplify the other bits. So you mustn't think that the state of each, the state in theory should be the same, because you're looking at atmosphere, you're looking at ocean, you're looking at the same basic processes, the same basic physics, but the way you structure your model will vary culturally depending on who's doing it. If it's an atmospheric physicist doing it, they'll probably say, well, actually nothing interesting happens in the ocean at all. We don't need to get that detail. An ocean person will say, these atmosphere people, they just don't understand oceans. They are so complex. You see the David Attenborough bit, it's so fantastic what goes on. The air just stays the same, So each model will be different, not just because even the points that are put in it will be done in a slightly different way, making slightly different assumptions. But the state of the model, these are real terms, technical terms, mean the variables that are being used. And the one that you talked about earlier, boundary conditions. Each model has to have a boundary. Although in reality there is no sort of boundary, in the sense you can go way out to the planets, but we know that the atmosphere stops at a certain level. But to run a model, you have to put it within a boundary. You have to encase it. And those boundary conditions are crucial to what you drive the model with, what you decide. So these boundaries all have properties, like the Earth's surface has a boundary, the albedo, roughness, heat capacity, which depends on land cover and assumptions about that. And the boundaries are always, and this is one reason why when you run a model, you also have the boundary that, you know, the Earth's been going on like this, and we suddenly say, right, we're going to stop it. You don't stop the Earth, but we do stop it for a model. We say we're going to run from now, or from 2015, January the 1st, 2015, to January the 1st, 2035. So we started at 2015. But of course, that's an arbitrary start, because the model's already running before, the real world is already running before that. So we have to make a starting, but where we make assumptions about what is, we simplify the reality to start it off. And so the boundary conditions, these are external to the model, but they determine the position of actual physical boundaries in the model domain, but also the initial conditions of the model as it's set up to run. So we make assumptions about those. And we drive it by forcing. The forcing variables. Now, the forcing variables, we know that solar radiation is the principal forcing variable. So we can drive that. We know what drives the Earth-ocean system, atmosphere system, is incoming solar radiation. So we can model, we can get a good idea what we think that might be. It's still that is, to drive it, we have to make assumptions about what's going to happen to solar energy. How do we make those assumptions? How do we assume what solar energy is going to be driving the Earth in 2030?
By looking at like previous models and seeing how like fluctuations and
Previous models?
or like looking observations.
Observations, right. So it's we use our understanding of the past. So this is why we're moving into within the module saying actually we need to know about the past, because that we're making. If we take solar radiation, and I briefly talked about this before, so talk about it next year. There is debate at the moment. Are we now going to enter a more de minimis equivalent, such that actually the amount of solar radiation variability is going to be lessened, and the amount of solar radiation is going to be low relative to previous highs. We have not a clue what solar radiation input will be in 2030. For all we know, we could be coming into a minimum whereby the cycle effectively stops, as it's done in the past. Our understanding of the past is such that we can't predict that. It is highly likely that solar variability, for instance, in the future, solar radiation is going to be low. That actually the peaks have gone lower and lower, and it's quite likely that in the next cycle, assuming that the cycles continue, that the peaks of those cycles will get low. So you have to make assumptions, but obviously if you think about that, the difference between making an assumption of a cycle that runs like that through time and one that runs like that through time, is quite significant to how the thing's going to run. And you don't know, you have to make an assumption about that. We also make assumptions, as you said, about what we do about anthropogenic gases, especially CO2 and methane. And we'll talk about this next week, about what sort of assumptions we make. But as a sort of introduction to that, when the IPCC and modelling first really took off, they did scenarios for greenhouse gas emissions. And the one that was the most extreme was called business as usual. In other words, we just didn't give a toss, just let it all carry on. And everybody, or the critics, said that is assuming that's been far too negative. And therefore you need to make assumptions about changing emissions that we actually begin to reduce these. The reality of it is that if you look at the models in the 1980s and the 90s and you look at their comparability to what's actually happened by now, it's business as usual that is the one that's measuring what's actually happened. But the point, and we'll talk about this in detail next week, this is not a scientific parameter. It's scientific in the sense that the CO2 is acting in a scientific way to interact with solar radiation, etc. But that is a cultural parameter. The amount of greenhouse gas emissions in 2030, 2020, 2015 is totally a cultural, social parameter. You're not going to stop driving. You're not going to stop flying, which is driving CO2. The Indians and the Chinese aren't suddenly going to turn around and say, you know what, I don't think we'll use coal. I'll just close all the power stations. They're not going to do that. It's an economic, but it's a cultural, social parameter. And this is where I've already started to hint at this issue with modelling, that it's a very scientific, inverted commas, phenomenon, but what drives models are assumptions. Assumptions about scientific processes, about our knowledge of basic physical processes and physical laws, which is fine. But what also drives our modelling to the future, solar radiation, that's science. But actually, the way you predict into the future is cultural, whether you are naturally pessimistic that, oh, we're going into a minimum, or whether you're an optimistic person who says, well, in the past occasionally it's that they've come back again, we don't know why, so let's assume that everything's going to get warm again. In a sense, that's a cultural thing. So once we go projecting the forcing variables, the driving data, those are cultural, economic, social decisions which drive the assumptions that you feed into models. And I think you need to be fully aware of that. Regrettably, this is where obviously human geographers begin to have a role to play, because effectively, sorry about that. Some of my best friends are human geographers. Not many, but a few. But effectively, they're saying, well, actually, the science is brilliant, but the reality of it is that the decisions that drive that are human, are cultural, are social. This is why I asked you the question, how far into the future should you run a model? Because I can tell you as a scientist, or I could tell you as a scientist, how much it would cost to run a model to 2100. And I could say, modelers can do it. They do it really well. It costs £2 million to run it, but it's no problem, technology is feasible.